The sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side.
That's a right triangle, you idiot!
In this video, we're going to look at the trig functions of the three special angles, which are 30, 45, and 60 degrees. Now, before we do that, we're going to do a quick review of what the trig functions actually do. So, given a right triangle, any right triangle, if I take a trig function of an acute angle, for example, this angle x is the acute angle of this right triangle, sine gives me a ratio of a certain set of sides. To help you remember which trig function gives you which ratio, we can use the acronym SOHCAHTOA. To help remind us. So sine gives us the ratio of the opposite side over the hypotenuse. In this case, the opposite side, the one across from the x, is 5, opposite, and the hypotenuse is always the side across from the right angle, with the adjacent side being the one adjacent to your reference angle x. So sine of this angle x will be the ratio of the opposite side of the hypotenuse, which in this case is 5/13. We also know that our calculator has the ability to calculate sine of a given angle measure. For example, say I wanted to know what sine of 26 degrees was. That would be if the ratio of the opposite and adjacent side given a 26-degree angle in that corner. Well, if I whip out a calculator, I can find sine of this angle, sine of 26 equals, and I get the ratio 0.43. Overall, there are two ways of calculating a trig relationship. Given a triangle, we can find the exact ratio, or we can use the calculator and it will give us an approximated value.
Alrighty then.
Those angles are 30, 45, and 60. Now I'm going to go ahead and tell you that the sine of 30 degrees is 1/2, the cosine of 30 degrees is the square root of 3/2, and the tan of 30 degrees is the square root of 3/3. Now first, let's see if that's actually true by checking with our calculator. If I type in sine of 30 degrees, I get 0.5, which is indeed 1/2. If I check the cosine of 30 degrees, I get 0.866. Well, my question is that actually equivalent to the square root of 3/2? Well, we can check that by finding out what the square root of 3/2 is. And notice that they are the exact same decimal value. The same would be true if I check tangent of 30 degrees against the square root of 3/3. Notice that those are both also the same decimal value. So then my question is, how do we know that this decimal value is actually this? And are they even related to each other? Well, the answer is yes. And it actually comes from a real subtle way of figuring out what these exact ratios are. So to find the exact value, recall that all trig values have to do with right triangles, and the only right triangle which has an acute angle of 30 degrees is the 30, 60, 90. Well, in a 30, 60, 90, all of its sides are in a constant proportional ratio. Across from the 30, that side is proportional to 1. Across from the 60, it's proportional to the square root of 3. And across from the 90-degree angle, or the hypotenuse, it's proportional to 2. It's in a 1 to rad 3 to 2 relationship. Well, now notice that for 30 degrees, I have my opposite side as 1. I have my adjacent side as rad 3. And I have my hypotenuse as 2. So if I wanted to know the exact value of sine of 30 degrees, I would look at the opposite over the hypotenuse, which gives me this 1/2. The cosine is the adjacent side over the hypotenuse, or rad 3/2, and the tangent is the square root of 3/3. Why? Well, remember that tangent from our SOHCAHTOA relationship, tan of 30 will be the opposite side over the adjacent side, which in this case is 1 over the square root of 3. But in math, we don't like to leave radicals in denominators, so we have to rationalize. I get rad 3 over rad 3 times this is my rationalizing factor, which gives me square root of 3/3. So that's actually where all these values come from. I'm just looking at the special right triangle that has a 30-degree angle in it. Since this triangle also has the 60-degree angle in it, if I rethink of this in terms of the 60-degree angle as my reference, when I'm looking at 60, the side opposite the 60 is the rad 3, and the side adjacent to the 60 is the 1. So sine of 60 would be opposite over hypotenuse. The opposite side from the 60-degree angle is the rad 3, so sine of 60 should be rad 3 over 2. Cosine of 60 is 1 over 2, or 1/2, and the tan of 60, tangent opposite over adjacent, is rad 3 over 1, or just square root of 3. For the 45 degrees, I could look at my other special right triangle, the isosceles right triangle, or the 45, 45, 90, and fill in its proportional lengths. It's in a 1 to 1 to square root of 2 ratio for each of its sides. So notice that since both angles are 45 degrees, it doesn't matter which one I use as my reference. So I'll just use this one, which makes this side opposite, this side adjacent, and this side across from the 90 always my hypotenuse. With those sides labeled, I can see that the sine of 45 is 1 over the square root of 2. But just like with my rad 3 situation earlier, when I look at sine of 45 equals 1 over the square root of 2, I again have to rationalize with a rationalizing factor of rad 2. 1 times rad 2 gives me square root of 2, and rad 2 times rad 2 gives me 2. So the sine of 45 is rad 2 over 2. Similarly, the cosine is 1 over rad 2, which we just saw actually rationalizes. So the sine and cosine values are actually the same, and tangent of 45, opposite over adjacent, is just 1. Now these angles actually show up so often in trigonometry that knowing their exact values can be extremely useful and time-saving. So I've become familiar with this chart over time.